All right. So what are we going to talk about this week? Kind of some filler stuff. It's a little bit of an eclectic week, so we're going to talk about various different things. We're going to put some of the AC that some of you learned to use, and then we're going to build a foundation to jump into magnetos next week. So we're going to start by talking about transformers. And not the kind that in the movie. Thank you.
Oh man, that's too bad.
I know.
I got so excited.
All right. So one big advantage. One big advantage. Big advantage of using AC, electrical power. Electrical power is the ability to use transformers to step up or step down voltage. Transformers to step up or step down the voltage. Now I chose to say step up or step down the voltage. I could have easily have just said step up or step down the current. So we're going to see how one affects the other. So what is a transformer? I'm glad you asked. Transformer is a device that is used to increase or decrease voltage in a circuit. So transformer is a device that is used to increase or decrease voltage. To increase or decrease voltage. In a circuit. I have another definition. A device that transfers energy from one circuit to another by electromagnetic induction. So it's two different definitions, both work. A device that transfers energy from one circuit to another. One circuit to another by electromagnetic induction. I'm going to see. Oh, that was definition. I should have put that here. 2, definition. There, now, because I have 3, and that's why it makes more sense. So let me tell you what a transformer consists of. Then I'm going to tell you how they work. A transformer consists of let me show you what a transformer looks like schematically. So I like the older style schematics. I told you that many times, instead of one that just looks like this. Because this represents what it really is. So it consists of a primary winding. What's a winding? It's coil. Yeah, it's coil wires. So where's my primary winding?
Larger wire. Depends on what you're trying to do.
It kind of depends on which side I'm looking from, but we'll call that the primary. If it's got a primary winding, it must have a secondary. Secondary winding. So that'd be B. And it usually has a core. Often the core is made out of soft iron. It is usually laminated. Usually laminated. Why is it made out of soft iron instead of like hardened steel or some sort of high carbon steel? Anybody know? Okay, so ferrous means something made out of iron. So ferrous, now keep in mind that soft iron is ferrous, it's made out of iron. Carbon steel is ferrous, also made out of iron, it just has carbon put in it to make it much harder.
Which is non-magnetic.
It's very magnetic.
Carbon is?
Oh, I don't know, carbon is not, but carbon
That's what
steel.
I'm talking about.
It's
Carbon.
mostly steel
Yeah.
with some carbon in it. So carbon steel, give me an example of something that's made out of carbon steel in aircraft.
An aircraft.
No, TSA took that away from you, so.
Way to go, MacGyver.
I know. Knife? No, in an aircraft. Bomb? No.
Just don't say hijack in an airport.
Yeah.
Please do.
Waiting for an answer. First semester students are off the hook. I'm looking this way. I have to look this way. What?
Like, that needs a high temperature,
The block?
The crankcase?
skill.
Anything to throw. It's a crankcase made out of. He's just like, yeah, I locked him up over. He sees that. It's aluminum. The crankcase is aluminum,
Yeah.
so that throws out ferrous.
No, carbon steel.
The cylinders,
The cylinders are made out of.
the inside lining maybe?
Boy, that's the worst example. I mean,
Rings from different
the what?
rings.
The crank
Mike,
shaft.
Dave, thank you. How about the biggest, most expensive part of an aircraft?
I said that like 20 minutes ago. What is that?
Well, you were talking about something else when you said it, though.
That wasn't. I literally said the crank.
20 minutes ago, I grew what? 20 minutes ago, we were on break. I didn't hear you. So yes, the crankshaft is made out of high carbon steel. I'm not even going to ask anymore. Okay, so why would it be made out of soft iron and not high carbon steel?
Better at conducting flux, or it's a better core for the oil.
It is a better, obviously. But you know what? That is how you answer a good Q&A when you're doing, or your oral and practical. Well, it makes it much better. Don't try it with me, because I'll just say, why? Why? I guess I have to tell you. All right. This will probably make more sense, actually, after we do non-destructive testing. But that's to do with permeability and how magnetism does work with iron. So you take something like a crankshaft and you magnetize it. It takes more magnetism to line up the domains and magnetize it. But once you do, it's locked in. It stays that way. And so you take more magnetism to try and get rid of it. But you take something that's soft iron, it easily magnetizes and it doesn't take quite as much magnetism. But once you remove the current, it dies off. So it doesn't stay magnetized. And so when we talk about doing non-destructive testing with magnetic particle, you can magnetize a crankshaft, it stays magnetized, and you can work with it in your medium and actually inspect it without putting it back in and giving it more current. But you take something soft iron core, you have to magnetize it while you're applying, run the current through a part while you're applying the medium to it, because as soon as you remove the current, the magnetism dies off. And you want that because you want, remember we're talking about AC, which is going to be constantly shifting directions. And if you don't have an soft iron core, you had something with high carbon steel, it doesn't want to shift directions. It takes too much current to shift it. So then you start getting these problems. So that's why you want it made out of soft iron, because it just to simply put, it allows the magnetic lines of flux to easily reverse inside of there. So that's our soft iron core.
Why would they typically laminate it?
Well, thank you for that segue. Notice that it's got two lines, but there's really only one core, right? So laminated means that you just take a whole bunch of thin pieces of this metal and you put them all together. So if you actually look at the core in the magnetos that you're working with, you'll notice that there's a whole bunch of laminations. Laminations, not lamentations. Those are two different things. You either get that or you don't. So laminations. Lamentations are like crying out, or something. It's woes, isn't it?
Hit the wall.
The woe. Laminations. Laminations prevent eddy currents. What's that?
It separates them by the layers. It's divided them by layers.
That is called laminations.
Yeah, but it's not preventing, just separate.
I don't know what you said. I'm not sure what you said. All right. So what are eddy currents? Eddy currents are small little circular currents within a conductor core. They add resistance, power loss, and heat, which is not a good thing. So what can I say? Eddy currents, they are eddy currents. Huh? Eddy. Like Eddie Munster or Eddy, E-D-D-Y. Eddy currents. Eddy currents are small. Yeah? What? Well, you called me. Eddy currents are small circular currents. Small circular currents within a conductor or core. And when we get into non-destructive testing, we're also going to talk about eddy current inspections, where you actually use eddy currents to inspect metal. So eddy currents add resistance. Eddy currents add resistance. Power loss. And heat. And those are bad. Put that bad. That's bad. Don't want that. Yeah.
Is that for determining the thickness of something without actually seeing, like, having the other side access to it?
Is it? No, it's
Is
not.
that for the eddy current?
It can be used for that. It's not
Okay.
necessarily what it is.
Yeah,
It's
that's what,
not
that's
what
what
it's
I've heard used for that.
not what it's not for, but yeah, you can determine thickness of metal. You can find small cracks. All right, so
What's the condition?
Uh-huh.
Say bad?
bad.
Okay.
You don't want that. Bad. I could have wrote undesirable, but that was a long word, and that would have taken too much time. So
Looks like bad.
B-A. You want to try writing with this thing? It's not easy. Bad. All right. So what's going on here? We have. We'll come back here. We'll just use all this space right here. All right. So I've got. Got a transformer. And we'll put a light right there. There we go. Transformer with a light. All right, so let's think about how we can make this work here. If I take and put some power on this, what is going to happen when... Where'd my eraser go? I thought it was right there.
It's over yonder.
What?
Right.
It's a different... I know, it's something changed. So this is usually...
That's the hard eraser.
I know, that one works better. See? It's better.
You can't get the soft one.
Yeah, I don't like the
It'll
soft
only
one.
erase it part-time.
All right, so even though it's red. All right, so I got a switch right there. So obviously, what am I going to have running through the circuit right now? How much amperage?
Zero.
Some of you are going, huh? Okay, so we got zero. What?
What?
This, is this AC or DC?
DC.
How can you tell?
You gotta
Goes
have
better.
it.
Okay, So we're going to slow time down. So very slow here. Slow time down. So I'm going to close the switch. And time goes very slow. So what's going to happen is current is going to flow through here. It's going to slowly come up to here. And whose law is that says as it builds up, it takes how long?
5 times.
Okay, so it takes 5 time constants, so it's going to build up. It's not instantaneous. And what is going to oppose the current coming in? I hear Lenz's law. I'm going to go with Lenz's law. L-E-N-Z. Lenz's law. It's going to oppose the current. But as this happens and current is flowing, what is going to be building up through here?
Magnetic field.
Okay, electromagnetic field, and it's going to radiate out in all directions. I'm just going to make it go to the right. It's going to radiate out. And as it radiates out, remember, it's building up. Building up is a change. So as this builds up, this field is expand. Remember, I'm going very slow. It expands out, and it cuts across the core and which winding?
Secondary.
Okay, it cuts across the secondary. So as it's cutting across the secondary, you can expect to see this light go because we're going to transfer energy. But because it's DC, it's going to build up and do what? Just stay. So as it stays, the magnetic flux is there, but it's not changing. There's no change. You must have change. It's stagnant. So it's built up, it's stagnant, so nothing happens. Now, if we open the switch, the field is going to collapse. Takes how long?
5 times.
All right, but it's going to collapse pretty dang rapidly, right? And a rapid, fast collapse of that field that had grown across the secondary is going to suddenly and rapidly collapse, which will induce a voltage over here.
It's like a magneto.
Over here. Why did I keep doing that? Over here. There we go. So it's going to induce a voltage over here, and the light will shine for a brief moment in time.
5 times 5.
About. All right. But that's all you're going to get with that. So it's only going to work twice. Once when you turn it on, and once when you turn it off. Well, how wonderful is that going to be? So basically what you have to do is you have to get a little monkey on the switch, and you have to constantly do that little thing. Or I could get a cam, something that rotates, and it makes the switch go up and down without the monkey. Huh? It's a 4-lobe cam. 1, 2, 3, 4. Yes, that's what I was trying to do. 4-lobe cam. So this is going to spin around, and it's going to constantly connect and disconnect. And as we do that, we will. Huh? Yes. What does this remind you of? Ignition points. I really did just draw an ignition system. Just make this into a spark plug over here. So this is how old-timey ignition systems actually worked. So instead of a light bulb, you would just put a spark plug. And instead of having equal amount of coils, you would have a certain amount here and a large amount over here. We'll talk about that in a little bit. But that transfers electricity over. So that's what's going on there. But we don't have to do it like that. We could change this around. And make that AC. And we can get rid of this. And we can just close the switch. And now we have AC. So it's going to first go one way, the current. It's going to build up through here. It is going to expand. Remember, while it's expanding, you have change. It's building up. And that is action. It is a electromagnetic field building across a wire. It's the same thing as moving the wire in a magnetic field. Now we're leaving the wire the same and just moving the magnetic field. Build it up, pull it back, build it up, pull it back, build it up, pull it back. So not only are you pulling it back, of course, but you go the other way. So it builds up one way, and then it changes polarity and builds the other way. So it's constantly cutting across this secondary system. So this light is just always going to be on. All right. So what did I just say?
A lot.
Is anything worthwhile? Principle of operation. All right, conductors have a magnetic field when current flows. If this magnetic field, if this magnetic field cuts, say cuts in quotes, cuts through a wire, and that would be not the same wire, but a different wire. If it cuts through a wire while expanding or contracting, expanding or contracting, induction happens. So what I've done up here in this drawing, I've induced a current in the secondary. So that's induction. So in a transformer, as AC is fed into the primary, I'm going to put parentheses, AC or, is it chopped DC. That's what I did with that little square that I put there and said it was a cam, or the monkey that was flicking the switch on, or one of my kids who play with the light switch, or Steve back there who plays with the light switch next to him. So that's what you're doing. You're doing chop DC, on, off, on, off. So in a transformer's AC or chop DC is fed into the primary. Into the primary, well, winding, I should say winding, comma. A magnetic field expands. The magnetic field expands out of the primary, that is, and field expands and contracts across the secondary. Well, I want to stick with my notes, so my notes are going that way. So let's do it this way. It is fed in the primary winding, a magnetic field expands and contracts around the primary. Let's say that. So we're talking just about the primary. So right now the primary is expanding and contracting a field. That's all I've really said in my notes. So you just have one thing happening, primary, expanding, contracting. We haven't even got to the secondary yet. But before we get to the secondary, it's time for a break. And thanks to Tim, I can hit the freeze button. Now you won't yell at me. I don't care about them.